There is a planet out there, somewhere in the darkness above your head, where the sky might glow a pale shade of red, where rain might be falling at this very moment onto rocks that no human eye has ever seen, where an ocean might be sliding back and forth against a silent shore under the light of a sun that is not our own. And the most unsettling part, the part that should make the hair on your arm stand up, is that NASA has already found places like this. Not in a movie, not in a dream. In real data collected by real telescopes pulled out of the faint, trembling light of distant stars. As you sit here breathing the air of the only world we have ever called home, there are worlds being cataloged, measured, and quietly added to a list. A list of planets where, under the right conditions, a human being might be able to stand, look up, and survive. This is the story of how we found them, what they are really like, and why the answer to the oldest question we have ever asked, are we alone, and is there anywhere else we could go, may be closer than anyone is comfortable admitting. To understand why this matters, you have to understand how impossibly hard it was even to imagine doing it. For almost the entire history of our species, the stars were just lights. Beautiful, fixed, untouchable lights. Every human who ever lived before the 1990s looked up at the night sky and could not say with any certainty whether a single one of those points of light had planets at all. We had our own sun, our own family of worlds, and beyond that, nothing but speculation. Philosophers argued about it. Poets wrote about it. But no one had ever seen another world orbiting another star because it was thought to be essentially impossible. A planet does not shine on its own. It only reflects the light of its star, and that reflected glow is staggeringly faint, like trying to spot a firefly hovering next to a lighthouse from thousands of kilometers away. The star's brilliance drowns everything out. For decades, the smartest people on Earth assumed we might never directly find another planet, let alone one we could live on. And then, in the span of a single generation, everything changed. The first confirmed planets around a sun-like star were detected in the mid-1990s, and the discovery was so strange that many astronomers refused to believe it at first. The world they found was nothing like Earth. It was a giant ball of gas, larger than Jupiter, whipping around its star so fast that its year lasted only a few days. It was scorching, bloated, utterly hostile. But it was there. It was real. And it proved beyond any doubt that our solar system was not unique. Other stars had planets too. The floodgates opened. Within a few years, dozens of new worlds were found. Then hundreds. Then the count climbed into the thousands. Each one was a pin dropped onto a map of the galaxy that, until that moment, had been almost entirely blank. And as the numbers grew, a question that had once belonged to science fiction began to feel like an engineering problem we could actually solve. Out of all these thousands of worlds, were any of them like ours? Were any of them the kind of place where life, or even people, could exist? The trouble is that a planet where humans could live is a far more demanding idea than most people realize. When you hear that phrase, your mind probably fills in a picture. Green hills, blue skies, a comfortable temperature, maybe an ocean in the distance. But the conditions that make Earth livable are absurdly specific, and almost everything has to go right at once. The planet cannot be too close to its star, or the heat will boil away every drop of water and leave behind a dead, scorched rock. It cannot be too far, or the water will freeze solid, and the surface will become a frozen wasteland colder than anything on Earth. It has to sit in a narrow band, a thin ring of space around the star, where the temperature is just right for liquid water to exist on the surface. Scientists call this the habitable zone, though it has picked up a more poetic nickname over the years. They call it the Goldilocks zone, not too hot, not too cold, but just right. And finding a planet that sits inside that zone is only the very first box on a long and unforgiving checklist. Because even a planet in the perfect orbit can be a death trap. Think about everything that has to be true about the Earth beneath you right now for you to simply be alive. The planet needs to be the right size. Too small, and its gravity is too weak to hold onto an atmosphere. The air simply drifts away into space over millions of years, and you are left with a thin, useless wisp of gas, or nothing at all, like Mars. Too large and the gravity becomes crushing. The atmosphere thickens into a suffocating blanket, and the pressure at the surface could flatten you. The planet needs a real atmosphere, and not just any atmosphere, it needs the right gases in the right amounts. Too much carbon dioxide and the whole world cooks under a runaway greenhouse effect, the way Venus did, until the surface glows hot enough to melt lead. Too little of the right gases and there is nothing to breathe, nothing to trap warmth, nothing to shield the surface from the lethal radiation pouring out of the star. And speaking of radiation, the planet almost certainly needs a magnetic field, an invisible shield generated deep in its molten core, deflecting the storm of charged particles that every star constantly blasts into space. Without that shield, the atmosphere gets stripped away and the surface gets sterilized. Earth has won. It is the reason you are still here. When you stack all of these requirements on top of one another, the dream of finding a livable world starts to feel almost hopeless. The right distance, and the right size, and the right atmosphere, and the right chemistry, and a magnetic field, and a stable star that does not flare violently, and liquid water, and probably a dozen other things we are only beginning to understand. The odds of all of that lining up on a single planet seem vanishingly small. And yet the galaxy is so unimaginably vast that even vanishingly small odds, multiplied across hundreds of billions of stars, can still produce a staggering number of possibilities. Our galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. If even a tiny fraction of them host a planet in the habitable zone, and the data we now have suggests it is far more than a tiny fraction, then the number of potentially livable worlds in our galaxy alone could be in the billions. Billions of Earths. The challenge was never really about whether they exist. The challenge was about finding them, identifying them, and figuring out which ones might actually be worth the unimaginable journey it would take to reach them. So how do you find a planet you cannot see, orbiting a star trillions of kilometers away, hidden in a blaze of light? This is where human ingenuity becomes almost breathtaking, because the methods scientists invented to do this are so clever they border on magic. The first great technique relies on a simple, beautiful idea. If a planet's orbit is lined up just right from our point of view, then once every orbit, that planet will pass directly in front of its star, crossing the face of it like a tiny shadow. When that happens, the star's light dims just slightly, just for a few hours. The dimming is minuscule, often less than 1%, sometimes far less. But it is regular. It repeats. Every time the planet comes around, the star blinks, ever so faintly. And by watching thousands of stars at once, continuously for years, and looking for those tiny, repeating dips in brightness, astronomers can detect the silhouettes of planets they could never directly see. This is called the transit method, and it became the single most powerful planet hunting tool ever devised. To use it on a grand scale, NASA built a machine specifically for the job and launched it into space where Earth's atmosphere could not blur its vision. It was called Kepler, named after the astronomer who first worked out the laws of planetary motion centuries ago. Kepler was, in a sense, the most patient instrument ever made. It pointed at a single patch of sky, a region containing more than 150,000 stars, and it simply stared. It did not look away. For years, it measured the brightness of every one of those stars, over and over, watching for the faint, telltale blinks that would reveal a hidden world. The amount of precision required was almost absurd. Kepler had to be able to detect a dimming so slight it was like noticing the change in a searchlight's brightness when a single moth flew across it. And it worked. It worked beyond anyone's wildest hopes. Kepler did not just find a few planets. It found thousands. It revealed that planets are not rare exceptions scattered thinly across the galaxy. They are everywhere. The data showed that, on average, nearly every star in the sky has at least one planet. Look up at any star tonight, any star at all, and the odds are overwhelming that it has worlds of its own circling it in the dark. But Kepler did something even more important than just counting planets. It found ones that were small. In the early years of planet hunting, almost everything discovered was a giant, enormous gas worlds, easy to detect precisely because they were so big. Finding a planet the size of Earth was a completely different challenge because a small planet blocks far less light when it transits, making its signal fainter and harder to pull out of the noise. But Kepler was sensitive enough to catch them. And one by one, it began to find them. Rocky worlds, Earth-sized worlds. And then, the Holy Grail, small, rocky, Earth-sized worlds sitting right inside the habitable zone of their stars. The first time that happened, it was a milestone in human history, even if most people barely noticed it on the news. For the first time ever, we had found a place that was, on paper at least, genuinely Earth-like. The right size, the right distance, the right temperature for liquid water. A real, physical location in our galaxy where, if you could somehow travel there, you might step out onto solid ground beneath a sky warmed by an alien sun. One of the most famous of these discoveries arrived with a name that sounds more like a serial number than a world, Kepler 452b. But the nickname it earned tells you everything about why it mattered. The scientists called it Earth's cousin. It was the closest thing to a true Earth twin that had ever been found at the time. It orbited a star remarkably similar to our own sun. Not a dim red ember, but a bright, yellow, sun-like star. And it sat squarely in that star's habitable zone, receiving an amount of light and warmth eerily close to what Earth receives. Its year, the time it took to circle its star once, was about 385 days, almost identical to our own 365. Think about that for a moment. On a planet over 1,000 light-years away, a year passes in almost exactly the same rhythm as it does here. If you lived there, you would barely have to adjust your calendar. And perhaps most astonishing of all, that planet had been completing those year-long orbits for billions of years, in some estimates even longer than Earth has existed. It was, potentially, an older, larger version of our own world, a glimpse of what Earth might look like a billion years from now, basking in the light of an aging star. Of course, there were caveats, and the scientists were always careful to point them out, because this is exactly the kind of story where excitement runs ahead of evidence. Kepler 452b was somewhat larger than Earth, possibly large enough to fall into a category called super-Earths, planets bigger than ours but smaller than the gas giants. We could not directly confirm that it was rocky rather than gaseous. We could not see its atmosphere. We could not know whether it actually had water, or a breathable mix of gases, or a protective magnetic field. From a distance of more than 1,000 light-years, all we could really measure was its size, its orbit, and the kind of star it circled. Everything else was inference and hope, and there was a darker possibility lurking in the data. Because Kepler 452b's star was older than the Sun, it had grown brighter and hotter over the eons, the way sun-like stars do as they age. Which meant that this world, even if it had once been a paradise, might now be in the early stages of the same catastrophe that will one day befall Earth. a slow, relentless heating that could be boiling away its oceans and pushing it toward a Venus-like fate. We may have found Earth's cousin at the worst possible moment in its life, like meeting a relative just as they begin to grow old and frail. Still, the significance of finding it could not be overstated. It proved that worlds like ours were out there, circling stars like ours, in orbits like ours. And it was just one of many. As Kepler kept staring and the data kept pouring in, the catalog of potentially habitable worlds grew and grew. There was Kepler 186f, the first Earth-sized planet ever confirmed in the habitable zone of its star, a world that orbits a cooler, redder sun than our own. There was Kepler 442b, which scientists came to consider one of the most promising habitable candidates of all, scoring even higher than some of the more famous discoveries on the various scales researchers use to rank a planet's potential to support life. There was Kepler 62f and Kepler 1649c, and a steadily lengthening list of names that the public never learned, but that on paper represented the most profound discovery in human history repeated over and over again. We were no longer asking whether other Earths existed. We were building a directory of them. But the planets Kepler found shared one enormous, frustrating problem. They were almost all impossibly far away. 1,000 light years, 1,200 light years, 2,000 light years. These numbers are so large that they cease to mean anything to the human mind, so let me try to make one of them real for you. A light year is the distance light travels in a single year, moving at 300,000 kilometers every second. In 1 year, light covers about 9.5 trillion kilometers. So a planet 1,000 light years away is 9.5 trillion kilometers from where you are sitting. With the fastest spacecraft humanity has ever built, a journey to a world like that would take not thousands, not tens of thousands, but tens of millions of years. The civilization that launched the ship would be long extinct before it arrived. These distant Earth twins were profound discoveries, proof that we are not alone in having a home, but they were not destinations. They were more like photographs of distant relatives we will never be able to visit. And so, even as the catalog of habitable worlds grew, a quieter and more urgent question began to take shape among scientists. Forget the 1,000-light-year giants for a moment. Is there anything closer? Is there a habitable world not across the galaxy, but right next door? The answer, when it came, was almost too good to be true, because the nearest star to our own sun, the closest stellar neighbor we have, the very next light in the cosmic darkness, turns out to have a planet in its habitable zone. The star is called Proxima Centauri, and it is part of a triple star system just over 4 light-years away. In cosmic terms, that is practically touching distance. It is the closest star there is, the first one we would ever reach if we set out to leave the solar system. And in 2016, astronomers announced that they had detected a planet circling it, a planet roughly the size of Earth, sitting in the zone where liquid water could exist. They named it Proxima Centauri b. For the first time, the dream of a habitable world was not an abstraction floating impossibly far away. It was right here, in our own cosmic backyard, around the very nearest star. If humanity ever builds a ship capable of crossing the gulf between stars, Proxima b is almost certainly where it would go first. It is the most natural destination imaginable, the closest possible foothold beyond our own solar system. To find it, scientists used a second great planet hunting technique, one even more subtle than watching for transits. It relies on the fact that a planet does not simply orbit its star like a marble circling a drain. The truth is more elegant. A planet and its star both orbit their shared center of mass, which means the star itself wobbles, ever so slightly, tugged back and forth by the gravity of the planet circling it. The star moves toward us a little, then away from us a little, in a repeating rhythm that matches the planet's orbit. And here is the genius part. When the star moves toward us, its light gets very slightly compressed, shifted toward the blue end of the spectrum. When it moves away, the light gets stretched, shifted toward the red. By measuring these tiny color shifts with extraordinary precision, astronomers can detect the wobble, and from the wobble they can deduce the presence of a planet they cannot see, along with an estimate of its mass. This is the radial velocity method, and it was sensitive enough to reveal Proxima b, a small world gently tugging at its star, betraying its existence through nothing more than the faint trembling of starlight. But before you start packing your bags, there is a complication, and it is a serious one. Proxima Centauri is not a star like our Sun. It is a red dwarf, a small, dim, cool star, far less massive and far less luminous than the Sun. Red dwarfs are by far the most common type of star in the galaxy, which is exciting because it means most of the planets in the universe orbit stars like this one. But red dwarfs have a temperament that makes them dangerous neighbors. Because they are so dim and cool, their habitable zone, the region where liquid water can exist, sits extremely close to the star. A planet has to huddle in tight to stay warm. Proxima b orbits its star far closer than Mercury orbits our Sun, completing a full year in just 11 days. And orbiting that close to a red dwarf is a perilous place to be, because red dwarfs are violent. They are prone to enormous, sudden flares, explosive bursts of radiation and charged particles that can erupt with terrifying frequency. A single one of these flares can be powerful enough to bathe a nearby planet in a dose of radiation that would be lethal to any unprotected life, and could, over time, strip away the planet's atmosphere entirely, leaving it as bare and dead as a stone. This is the central paradox at the heart of the search for habitable worlds, and it is worth sitting with for a moment because it shapes everything. The most common stars in the universe, the red dwarfs, are also the easiest places to find Earth-sized planets in the habitable zone, because the planets orbit so close and tug so hard and transit so often. But those same stars are temperamental and prone to flaring, throwing into question whether their planets could ever truly hold onto an atmosphere and shelter life. So a planet like Proxima b sits in a kind of agonizing uncertainty. It is the right size. It is in the right place for liquid water. It is unbelievably close by cosmic standards. And yet we genuinely do not know whether its surface is a temperate world with oceans and a sky, or a radiation-scoured rock that lost its air a billion years ago. Both are possible. Both are consistent with what little data we have. From 4 light-years away, we simply cannot yet tell the difference. And there is one more twist that makes Proxima b stranger still. Because it orbits so close to its star, it is almost certainly tidally locked, meaning one side of the planet permanently faces the star while the other faces eternal darkness, the way the moon always shows the same face to Earth. One hemisphere of Proxima b would be locked in perpetual day, the other in endless frozen night, with a thin band of permanent twilight running between them where, just maybe, the conditions could be survivable. Imagine standing in that twilight zone. The sun would never rise and never set. It would simply hang there, fixed on the horizon, a swollen red orb casting long, unchanging shadows across the landscape. Behind you, the world would plunge into freezing darkness. Ahead of you, it would blaze under relentless heat, and you would be standing on the only livable sliver of the planet, a ring of eternal dusk circling the entire world, where the temperature might just be right for liquid water and breathable air. It is one of the strangest places the human imagination has ever been asked to contemplate, and it might be real right now, just over 4 light-years away. We do not know, but we are getting closer to finding out, because a new generation of instruments is finally giving us the power to do something we could never do before. Not just to find these worlds, but to actually study them, to peer into their atmospheres and read the chemistry of their skies from across the void. Before we get to that revolution, though, there is one more system you have to hear about, because it is perhaps the single most extraordinary discovery in the entire history of the search for habitable worlds. In 2017, NASA held a press conference that sent a jolt through the scientific community and made headlines around the planet. Astronomers had been studying a small, dim, ultra-cool red dwarf star about 40 light-years away. A star so faint you cannot see it with the naked eye, so small it is barely larger than the planet Jupiter. The star was called TRAPPIST-1, named after the telescope that first spotted hints of planets around it. And what the astronomers found when they studied it closely was almost unbelievable. This single tiny star was not host to one planet or two or three. It was host to seven. 7 planets, all roughly the size of Earth, all rocky, all packed into a tight, intricate orbital dance around their dim little sun. And of those 7 worlds, several sat within or near the habitable zone, in the region where liquid water could potentially exist on their surfaces. 7 Earth-sized planets around a single star. Nothing like it had ever been found. The TRAPPIST-1 system is so compact that all 7 planets orbit closer to their star than Mercury orbits our Sun. The entire system would fit comfortably inside the orbit of our innermost planet. The planets are so close to one another that if you were standing on the surface of one of them, the others would loom in the sky, visible as disks, some of them appearing larger than the moon looks from Earth. You could look up and see neighboring worlds hanging overhead, their surfaces faintly visible, close enough that they almost feel touchable. The planets are locked into a beautiful, mathematically precise rhythm called orbital resonance, where their orbital periods form near-perfect ratios, each planet's year a neat fraction of its neighbors. They tug on one another with their gravity in a delicate gravitational ballet that has kept them stable for what may be billions of years. It is one of the most elegant arrangements ever discovered in the cosmos, and it turned a faint, anonymous red dwarf into one of the most famous and most studied objects in the entire sky. What makes TRAPPIST-1 so important for our story is not just the number of planets, but the fact that several of them are in the habitable zone at once. 3 of the 7 worlds sit in the region where the temperature could allow liquid water on the surface. That means a single star system, just 40 light-years away, contains not 1 but potentially 3 candidate worlds for life. And they are close enough to one another that, in principle, life, or even a future human presence could spread between them. Of these, the planets often singled out as the most promising are the ones in the middle of the system, where the balance of warmth seems most favorable, where models suggest water might pool into oceans and lakes rather than boiling off or freezing solid. The names are unromantic. TRAPPIST-1e is frequently named as the standout, the world most likely to be genuinely Earth-like, with a density and size that suggest a rocky composition and a temperature that could allow for a temperate surface. Some studies have ranked it among the most habitable exoplanets ever found, a small, rocky world bathed in the gentle red glow of its tiny sun, where, just maybe, an ocean reflects a sky we can only imagine. And here is what makes TRAPPIST-1 not just a beautiful curiosity, but a genuine target for investigation. Because these planets transit their star, passing in front of it from our point of view, we have a way to study their atmospheres directly. When a planet with an atmosphere passes in front of its star, a tiny fraction of the star's light filters through the thin shell of gas surrounding the planet on its way to us. and different gases absorb different colors of light. So if you can capture that filtered starlight and split it apart into its spectrum of colors with enough precision, you can read which gases are present in the planet's atmosphere, like reading a barcode written in light. The dark gaps in the spectrum, where certain colors are missing because they were absorbed by gases in the alien sky, are a chemical fingerprint of that distant world's atmosphere. This technique, called transmission spectroscopy, is the closest thing we have to actually visiting these planets. And for most of human history, it was completely impossible. The starlight is too faint, the signal too subtle, the atmosphere's too thin. We simply did not have an instrument powerful enough to do it. Until, after decades of work and billions of dollars and more delays than anyone wants to remember, we finally built one. That instrument is the James Webb Space Telescope, and its launch marked the beginning of an entirely new chapter in the search for livable worlds. For decades, the Hubble Space Telescope had been our great eye on the universe, and it was a marvel, but it had limits. James Webb was built to see what Hubble could not. It is far larger, with a golden mirror more than 6 meters across, unfolded in space like the petals of an enormous flower. And crucially, it was designed to see in infrared light, the longer wavelengths that are invisible to the human eye but that carry the chemical signatures of molecules in planetary atmospheres. Infrared is the language in which planetary skies speak, and James Webb was built to listen. It was launched on the final day of 2021, after years of delays and a development saga so fraught that many people doubted it would ever fly. It traveled to a special point in space about 1.5 million kilometers from Earth, far beyond the moon, where it could sit in permanent cold and darkness, shielded from the sun's heat by a sunshade the size of a tennis court. And then it opened its eye and began to look, and almost immediately, it started doing something no telescope in history had ever managed to do reliably. It began to read the atmospheres of planets orbiting other stars. The power this gave us is hard to overstate. For the entire history of exoplanet science up to that point, we had mostly been counting worlds and measuring their sizes and orbits. We could say that a planet existed, that it was a certain size, that it sat at a certain distance from its star. But the most important questions, what is it made of? What is in its air? Could anything live there? Remained almost entirely out of reach. James Webb changed that. With it, scientists could begin to actually analyze the chemistry of distant atmospheres, to detect water vapor, carbon dioxide, methane, and other gases in the skies of worlds trillions of kilometers away. It was as if, after centuries of seeing only the silhouettes of distant lands, we had suddenly developed the ability to taste their air. And one of the first places scientists pointed this incredible new instrument was, of course, toward the worlds that might be able to support life. Among the most tantalizing targets was a planet that has become the center of one of the most exciting and contentious debates in modern astronomy. It is called K2-18b, and it sits about 120 light-years from Earth. K2-18b is not a perfect Earth twin, far from it. It is significantly larger than our planet, big enough to fall into a category that scientists have come to call sub-Neptunes, or, more intriguingly, a possible new class of world nicknamed Hycean planets. The idea behind a Hycean world is genuinely thrilling. It is a planet that might be covered by a vast, deep, global ocean of liquid water, wrapped in a thick atmosphere rich in hydrogen. Such a world could potentially be habitable across a much wider range of conditions than a planet like Earth, a great warm sea world stretching from pole to pole beneath a hazy sky. And K2-18b sits in the habitable zone of its red dwarf star, in the region where the temperatures could allow that ocean to exist as liquid rather than ice or steam. When James Webb turned its gaze toward this distant water world, it found something remarkable. In the atmosphere of K2-18b, the telescope detected the chemical fingerprints of carbon-bearing molecules, methane and carbon dioxide. That alone was a significant achievement, a demonstration that we really could read the air of a habitable zone world over 100 light-years away. But it was what came next that set the scientific world on fire. Some researchers reported a tentative, preliminary hint of another molecule in that alien atmosphere, a molecule called dimethyl sulfide. And here on Earth, dimethyl sulfide is produced almost entirely by life. It is released by marine phytoplankton, the tiny living organisms that fill our oceans. It is, in a very real sense, the smell of the sea. And it is a smell that, as far as we know, only living things create. If dimethyl sulfide were truly present in the atmosphere of K2-18b in significant quantities, it would be one of the most extraordinary findings in the history of science, because it would be a potential biosignature, a chemical clue that life itself might be present on a world beyond our solar system. Now, this is the moment where I have to be very careful and very honest with you, because this is exactly the kind of discovery that gets distorted and exaggerated, and the truth is more interesting than the hype anyway. The detection of dimethyl sulfide on K2-18b was, and remains, deeply uncertain. It was a faint signal, hovering at the very edge of what the telescope could measure, the kind of result that could easily turn out to be noise, or a misinterpretation, or a different molecule mimicking the signature. The scientists who reported it were appropriately cautious, stressing that it was a tentative hint and not a confirmation, and other researchers have since questioned whether the signal is even real. Furthermore, even if the molecule is genuinely there, it is not necessarily proof of life. Scientists have begun to explore whether dimethyl sulfide could be produced by non-living chemical processes under exotic conditions we do not fully understand. So this is not a discovery of alien life. Let me say that as plainly as I can. We have not found life on K2-18b, but what we have done is even more profound in its own way. We have reached the point, for the first time in human history, where we can actually go looking for these signatures, where the question of life on another world has moved out of philosophy and into the realm of measurement. We are now able to point an instrument at a distant ocean planet and ask, in the language of chemistry, is anything alive down there? We could not do that 10 years ago. We can do it now. And K2-18b is just one target among many. James Webb and the instruments that will follow it are slowly working their way through a growing list of candidate worlds, sniffing their atmospheres, cataloging their chemistry, building up a picture of what these planets are really like. With every observation, the fog lifts a little more. We are moving from an era of simply finding planets to an era of truly characterizing them, of knowing not just that they exist, but what they are made of, whether they have air, whether they have water, whether they bear the chemical traces that might hint at life. This is, without exaggeration, one of the great scientific frontiers of our time, and it is unfolding right now, in observations being made as you watch this. There are other nearby worlds, too, that keep the dream of a livable destination alive. Not long after launching its planet-hunting successor to Kepler, a spacecraft called TESS, designed to survey the whole sky and focus on the closest, brightest stars, NASA announced the discovery of a world called TOI 700d. What made this one special was that it was an Earth-sized planet in the habitable zone of its star, and it was relatively close, only about 100 light-years away, orbiting a quiet red dwarf that appeared to be calmer and less prone to violent flaring than many of its kind. A small, rocky, Earth-sized world in the habitable zone, around a star that might actually be stable enough to let it keep its atmosphere. That combination is exactly what scientists dream of finding. Later observations even revealed a second potentially habitable world in the same system. These are the kinds of discoveries that rarely make front-page news, but that quietly expand the list of places where, someday, humanity might find a foothold among the stars. When you step back and look at the full sweep of what has been found, the picture is genuinely staggering. In the span of a single human lifetime, we have gone from not knowing whether any other star had planets at all, to having confirmed the existence of more than 5,000 of them. With thousands more candidates awaiting confirmation, we have found gas giants and rocky worlds, scorching infernos and frozen wastelands, planets made of diamond and planets where it might rain molten glass, planets orbiting two suns at once like the fictional worlds of science fiction, and planets drifting alone through the darkness with no star at all. And nestled within that vast and bewildering menagerie, we have found a special and precious subset: the small, rocky worlds sitting in the habitable zones of their stars. The planets where, under the right conditions, liquid water could flow and life could take hold. We have found dozens of them already, and the statistics suggest that our galaxy contains billions more. The phrase that scientists use almost casually now would have been unthinkable to any astronomer just a few decades ago. Earth-like planets, they say, are common. There is nothing special about our world's existence. The universe makes worlds like ours all the time. Before we confront the hard limits of all this, let us linger a little longer on the sheer strangeness and beauty of the worlds we are talking about, because it is easy to let them become abstractions, names, numbers, catalog entries, when in truth each one is a place, as real and physical as the ground beneath you, with its own landscapes and its own skies and its own slow turning of time. Think again about what it would mean to stand on a planet orbiting a red dwarf, one of those small, cool, crimson stars that host most of the habitable zone worlds we have found. The sun in that sky would not be the small, fierce, blinding white-yellow disk we know. It would be enormous, swollen, hanging low and deep red, perhaps 3 or 4 times the width our sun appears in our sky, and dim enough that you could very nearly look at it without flinching. The light it cast would be the color of a perpetual sunset, a deep ember glow soaking the whole landscape in shades of red and rust and shadow. Plants there, if they existed, might not be green at all. Green plants evolved to harvest the particular light of our yellow sun, and under a red star, photosynthetic life might have evolved to be black or dark red, or some color we have never seen in a leaf, drinking in every scrap of the feeble infrared heavy light. The whole world would feel dim and warm and red, a landscape lit as if by the last light of a dying day that never quite ends. And if that world were tidally locked, as so many red dwarf planets are, the strangeness would deepen further. Time itself would behave differently. There would be no days and nights as we know them, no rising and setting sun, no morning or evening. On the bright side, the sun would simply hang fixed in the sky forever, never moving, blazing down on a single eternal noon. On the dark side, an endless, frozen, starlit night that never breaks, where the only light comes from the stars and perhaps the faint glow of distant aurorae. And in between, that ribbon of permanent twilight circling the entire planet, where the sun sits forever on the horizon, where the temperature might be mild enough for liquid water and breathable air, where weather would be driven by the eternal flow of heat from the scorching day side to the freezing night side, generating perpetual winds and storms along the boundary. If life arose on such a world, it would cluster in that twilight band, in the only zone where conditions allowed it, a thin ring of habitability wrapped around a planet of fire and ice. It is a vision so alien, so unlike anything in our own experience, that it strains the imagination. And yet it may be one of the most common kinds of habitable world in the entire galaxy, since red dwarfs so vastly outnumber stars like our sun. This is one of the quiet gifts of the search for habitable worlds. It has forced us to expand our imagination far beyond the narrow template of Earth. For a long time, when people pictured a livable planet, they pictured a copy of our own: blue skies, white clouds, green fields, a yellow sun. But the worlds we are actually finding are far stranger and far more varied than that. There are the twilight worlds of red dwarfs. There are the possible Hycean ocean worlds like K2-18b, drowned beneath global seas under thick hydrogen skies. There are super-Earths with crushing gravity and atmospheres unlike anything in our solar system. There are planets orbiting two stars at once, where double sunsets paint the sky, and planets in tight, resonant chains like TRAPPIST-1, where neighboring worlds loom overhead like moons. Habitability, it turns out, may come in many forms, most of them nothing like home. And that realization carries a strange kind of hope, because it means the number of places where some form of life might find a foothold is far larger than we once assumed. Life does not necessarily need a carbon copy of Earth. It may only need liquid water, an energy source, and time. And those ingredients, in one configuration or another, appear to be scattered abundantly across the galaxy. But here is where the story has to confront a hard and humbling truth, because the gap between finding a habitable world and actually being able to live on one is almost unimaginably vast. When the headlines proclaim that NASA has found a planet where humans could live, they are using that phrase in a very specific and limited sense. What they really mean is that the planet sits in the habitable zone, where the temperature could in principle allow liquid water. That is an extraordinary thing, but it is a far cry from a world you could actually step out onto and breathe. Consider what habitable has meant in our own solar system. Mars sits at the edge of the Sun's habitable zone. By the loose definition used for distant exoplanets, Mars might be flagged as potentially habitable. And yet Mars is a frozen, airless desert, its thin atmosphere unbreathable, its surface bombarded with radiation, its temperatures plunging far below anything humans could survive without protection. If an alien astronomer 100 light-years away detected Mars in our system, they might add it to their list of promising habitable worlds, never knowing that its surface is a lethal, lifeless waste. This is the sobering reality. Being in the habitable zone is necessary, but it is nowhere near sufficient. For a planet to be truly livable for human beings, not just for hardy microbes, but for people who need to breathe and eat and not be cooked by radiation, an astonishing number of conditions all have to be satisfied at once. Start with the atmosphere. Earth's air is about 21% oxygen, and that oxygen did not just happen to be there. It was put there by life, by billions of years of photosynthesis, by plants and microscopic organisms slowly pumping oxygen into the air. A planet with no life would likely have no free oxygen at all, which means that even a perfectly temperate world with liquid oceans might have an atmosphere you could not breathe for more than a few seconds. The very thing that makes our air breathable is a product of the biosphere it sustains. So a habitable zone planet without an established ecosystem might be, from a human standpoint, as suffocating as the surface of Venus, even if its temperature were pleasant and its oceans were full. You cannot simply walk out onto an alien beach and inhale. The air would have to have been transformed by life over eons before it could ever support a creature like you. Then there is the matter of gravity. Many of the most promising worlds we have found, including some of the famous super-Earths, are larger and more massive than our own planet. On a world with significantly stronger gravity, everything would feel heavier. Your own body would feel heavier. Walking would be exhausting. Over a long period, the strain on the human heart, bones, and muscles could become a serious health problem. And building anything, rockets, structures, vehicles, would be far harder against a deeper gravitational well. A planet with much weaker gravity poses the opposite problem, the one that haunts Mars. It cannot hold onto a thick atmosphere, and over geological time its air leaks away into space. There is a narrow band of planetary size and mass, where the gravity is strong enough to keep an atmosphere but gentle enough for a human to live comfortably, and not every promising world falls inside it. Earth, it turns out, may be unusually well suited to us, not by coincidence, but because we evolved precisely to fit it. We are not generic creatures who could thrive anywhere with water and warmth. We are exquisitely tuned to the specific conditions of this one planet, and a world that is merely similar might still be subtly, fatally wrong for us in a dozen ways. Consider the star, too. We have already seen that red dwarfs, the most common hosts of habitable zone planets, are prone to violent flares that could strip atmospheres and sterilize surfaces. But even setting flares aside, the light from a red dwarf is different from the light of our sun. It is redder, dimmer, weighted toward the infrared. Plants on Earth evolved to harvest the specific wavelengths our yellow sun produces. Under the light of a red dwarf, photosynthesis as we know it might work very differently, or struggle, or require entirely different biochemistry. The landscape under a red sun would be alien in ways that go beyond mere color. The whole rhythm of life, the energy available, the way warmth is distributed, the very chemistry of the surface, would be shaped by a star that behaves nothing like our own. And around stars that are larger and hotter than the sun, there is a different problem. Those stars burn through their fuel quickly and die young, often not lasting long enough for complex life to slowly evolve on their planets the way it did over billions of patient years here on Earth. The sun, it turns out, sits in a kind of sweet spot, stable, long-lived, gentle, the right color and temperament to nurture a world over the immense spans of time that life seems to require. Not every star is so accommodating, and we have not even reached the hardest problem of all, the one that towers over every other obstacle, and that no amount of scientific discovery has yet been able to overcome. Distance. The sheer, crushing, almost incomprehensible distance between us and even the nearest of these worlds. Let us go back to Proxima b, the closest habitable zone planet to Earth, just over 4 light-years away. That is the best case, the nearest possible destination, and it is already a journey that defies belief. The fastest spacecraft humanity has ever launched, traveling at the blistering speeds we can currently achieve, would take tens of thousands of years to cover that distance. Tens of thousands of years. Civilizations rise and fall over such time scales. The entire recorded history of humanity, from the first written word to this very moment, fits comfortably within a span shorter than that journey. A ship launched today toward Proxima b, using anything close to current technology, would still be traveling long after everyone alive today, and their descendants for hundreds of generations, had lived and died. The people who arrived would be the distant offspring of the people who left, born and raised entirely in the dark between the stars, having never seen the Earth their ancestors departed from. This is the great filter that stands between us and these worlds, and it is not a problem of will or ambition or funding. It is a problem of physics. The universe is built on a scale so vast that even light, the fastest thing there is, takes years to cross the gaps between the nearest stars and tens of thousands of years to cross the galaxy. And nothing with mass, no ship, no person, no probe can travel as fast as light. The faster you try to go, the more energy it takes, and the energy required to push a spacecraft to even a fraction of light speed is staggering, far beyond anything our civilization can currently produce. Scientists and engineers have dreamed up ways it might be done someday. There are concepts for ships driven by controlled nuclear explosions, by fusion engines, by vast sails pushed by powerful lasers fired from our own solar system. There are ideas, still entirely theoretical, about whether the fabric of space itself might one day be manipulated to shorten the journey. But all of these remain dreams, sketches on the drawing board of the future. For now and for the foreseeable future, the habitable worlds we have found remain tantalizingly out of reach, close enough to study, close enough to imagine, but far, far too distant to visit. So why does any of this matter, you might ask, if we can never go there? Why should it stir anything in us to learn that there are livable worlds we cannot reach? The answer, I think, goes deeper than the practical question of travel, and it touches something fundamental about what it means to be human and to be conscious in this universe. For the entire span of our existence, we have looked up at the stars and wondered whether we were alone, whether this small blue world was a singular miracle, a cosmic accident never to be repeated, or whether the universe was filled with other homes, other Earths, perhaps even other minds looking back at us across the dark. And for all of that time, we had no way to know. The question was beautiful and unanswerable, the kind of thing you could only sit with under a clear night sky and feel the weight of. But in our lifetimes, in the last few decades, that has changed. We have begun for the first time to actually answer it. And the answer so far is that we are not the only world like ours. The universe is full of Earths. The galaxy is dense with habitable zones and rocky planets and worlds where water could flow. We are not a unique miracle. We are one note in an enormous chorus, one home among billions of possible homes scattered across the sky. There is something profoundly moving about that realization, and also something that reframes our entire relationship with the cosmos. If habitable worlds are common, then the raw materials for life, and perhaps life itself, may be common too. And that leads inevitably to the deepest question of all, the one that hides behind every exoplanet discovery, behind every atmospheric measurement, behind every faint hint of dimethyl sulfide in a distant alien sky. Are we alone? Not just is there another planet like Earth, but is there anyone on it? Is there life out there looking up at its own night sky, wondering the same thing about us? The search for habitable planets is, at its heart, the search for an answer to that question. Every world we add to the catalog is another place where the experiment of life might have run a second time, another roll of the cosmic dice. And with each one, the odds that we are truly alone, the only living thing in a galaxy of 400 billion stars, grow a little more remote. The numbers are simply too large, the habitable worlds too numerous, for our isolation to feel certain anymore. Of course, finding a habitable planet and finding life on it are two very different things, and we have to resist the temptation to leap from one to the other. A planet can have liquid water, a temperate climate, a thick protective atmosphere, and still be utterly barren, a sterile paradise where life simply never got started. We do not yet know how easily life begins. Here on Earth, it seems to have appeared remarkably quickly, almost as soon as the planet cooled enough to allow it, which some scientists take as a hopeful sign that life arises readily wherever conditions permit. But we have only this one example to go on, and a sample size of one is a treacherous thing to build conclusions on. It is entirely possible that the origin of life is an exceedingly rare event, a fluke so unlikely that it has happened only once in the entire galaxy, or even the entire universe. Or it might be that life is everywhere, springing up on every suitable world, filling the cosmos with oceans of microbes and forests of strange plants and creatures we cannot begin to imagine. The truth is, we do not know, and that uncertainty is precisely why the work of telescopes like James Webb is so important. Every atmosphere we analyze, every biosignature we search for, brings us closer to the answer. We are, for the first time in history, in a position to actually find out. And here is a thought that I find genuinely staggering when I sit with it. The light that James Webb collects from these distant worlds left those planets long ago, in some cases, decades or centuries before it reaches us. When we look at a planet 100 light-years away, we are seeing it as it was 100 years ago. The chemistry we measure in its atmosphere is the chemistry of its past. If there is life there, if there is something stirring in those distant oceans, we are watching its ancient history play out in light that has been traveling toward us across the void since before we were born. And by the same token, the light leaving Earth right now, carrying the chemical signature of our own oxygen-rich, life-soaked atmosphere, is streaming outward in every direction, a beacon announcing the presence of a living world, spreading across the galaxy at the speed of light. If there is anyone out there with instruments like ours, they could, in principle, detect us. They could read the barcode of our sky and know that something here is alive. We are not just searching, we are also, simply by existing, a signal. A message written in the air of our planet, broadcast endlessly into the dark. Let us return for a moment to those specific worlds because they deserve to be more than names and statistics. They deserve to be imagined. Picture Proxima b, just over 4 light-years away, the nearest of all. Picture standing in that band of eternal twilight, the red sun fixed forever on the horizon, the landscape painted in deep crimson and shadow. Behind you, ice. Ahead of you, scorching desert. And all around you, the strange stillness of a world that does not turn, where there is no dawn and no dusk and no passage of day into night. Only the unchanging glow of a sun that never moves. Picture TRAPPIST-1e, 40 light-years away, its dim red star low in the sky, its sister planets hanging overhead like enormous moons, close enough to see their continents and clouds, a whole family of worlds wheeling around a single tiny ember of a star. Picture K2-18b, 120 light-years distant, possibly a vast and endless ocean stretching from horizon to horizon, its surface heaving under a thick, hazy, hydrogen-rich sky. And somewhere down in those alien depths, just maybe, the faint stirrings of something alive, exhaling the chemical breath that we strain to detect across the impossible gulf of space. These are not fantasies. These are real places. They have real coordinates in the sky. You could point a telescope at them tonight. They are out there right now, going through their days and their years and their slow geological seasons, completely indifferent to the fact that on a small blue planet 100 light-years away, a curious species has finally grown clever enough to notice them. For billions of years they spun in the dark, unknown and unseen. And now, in the span of a single human generation, we have found them. We have named them. We have begun to read their skies. It is one of the most remarkable transitions in the history of our species. The moment when the other worlds stopped being abstractions and became destinations, when the night sky stopped being a ceiling of fixed lights and became a map of places, real places, where the conditions for life, and perhaps even for human survival exist. What happens next is one of the great open questions of our age, and the honest answer is that nobody knows. It is possible that within the next few decades, as our telescopes grow more powerful, we will detect an unambiguous biosignature in the atmosphere of one of these worlds, a combination of gases that simply cannot be explained by anything other than living organisms. If that happens, it will be one of the most important moments in the history of human thought, the day we learned, for certain, that we are not alone. It would change religion, philosophy, science, and our entire sense of our place in the universe. Whole new generations of instruments are already being designed with exactly this goal in mind. Telescopes even larger and more sensitive than James Webb, observatories specifically built to hunt for the fingerprints of life on distant worlds. The search is accelerating, not slowing down, and many of the scientists working on it believe that if life is out there to be found, we may find the first signs of it within our own lifetimes. Not centuries from now, years, maybe a decade or two. The answer to humanity's oldest question may arrive while you are still alive to hear it. To appreciate how astonishing this all is, it helps to remember just how recently this entire field of knowledge did not exist at all. Go back only a little more than 30 years, and the number of confirmed planets known to exist outside our solar system was exactly 0. Not few, 0. Every textbook, every encyclopedia, every classroom on Earth could speak only of the 9 planets of our own sun. And beyond that, the honest answer to whether other stars had worlds was a shrug. We did not know. We suspected, we hoped, but we did not know. A child born at the dawn of the 1990s entered a world in which not a single planet beyond our sun had ever been confirmed. And that same person, now barely into middle age, lives in a world where we have cataloged thousands of them, measured their atmospheres, and begun to search them for the signatures of life. There are very few moments in the entire history of human knowledge where a question that had stood open for all of recorded time was decisively answered within a single lifetime. This is one of them. We are the generation that found the other worlds. Everyone who came before us could only wonder. Everyone who comes after us will take their existence for granted. We are standing right at the hinge of that transformation, and most people walking around today barely realize it happened. And the pace is only quickening. The instruments we have now, as powerful as they are merely the beginning. Already, astronomers are building a new generation of ground-based telescopes so enormous that their main mirrors stretch tens of meters across, giants that will gather far more light than anything that has come before, sharp enough to tease apart the faint glow of a planet from the overwhelming glare of its star. And in space, the dream that drives many of the scientists in this field is a future observatory designed from the ground up for one purpose above all others: to find another Earth and to determine whether it is alive. The concept goes by different names as it evolves, but the goal is always the same: a telescope powerful enough to directly image a small, rocky, habitable zone planet around a sun-like star, to block out the blinding light of the star itself and capture the faint reflected light of the world beside it, and to split that light apart and read its chemistry in search of the gases that betray the presence of a living biosphere. Oxygen, ozone, methane, water, the chemical fingerprints of life as we know it. Such an instrument could do what no telescope today can quite manage: not just find a habitable world, but tell us, with real confidence, whether someone is home. The plans for these observatories are being drawn up right now. The people who will operate them may already be in school. The discovery that changes everything may already be on its way. There is a particular kind of vertigo that comes from contemplating all of this. We are a species that, for almost its entire existence, was confined to the thin skin of a single planet, knowing nothing of what lay beyond. We evolved on the African savanna, we spread across the continents, we built civilizations, and through all of it, the stars remained a mystery beyond any hope of understanding. And now, in an eye blink of geological time, we have not only learned that the stars are other suns, and that those suns have worlds, but we have begun to study those worlds individually, to know their sizes and their orbits and the gases in their skies, to rank them by their potential to support life, to imagine standing on their surfaces. The leap is so enormous that it can be hard to take in. It is the difference between a person who has never left their village and a person who holds a detailed map of distant continents they will never visit but whose existence they can prove. We have become cartographers of the impossible, map makers of worlds we can never reach. And there is something both triumphant and aching about that, the triumph of having found them, the ache of knowing how far away they remain. That ache, the gap between knowing and reaching, may be the defining tension of our species for centuries to come. Because make no mistake, the dream of actually going does not die just because the distances are crushing. Throughout history, every barrier that seemed absolute eventually fell to human ingenuity and stubbornness. The oceans seemed uncrossable until they were crossed. The sky seemed unreachable until we flew. The moon seemed impossibly far until 12 human beings walked upon it. Interstellar distances are a barrier of a different order of magnitude, a challenge so vast it may take centuries or millennia to overcome, if it can be overcome at all. But there are serious scientists and engineers who spend their careers thinking about exactly this, who sketch out the designs for ships that might one day make the crossing. Some imagine enormous vessels, generation ships, that would carry not a single crew but an entire community across the void, with people being born, living their whole lives, and dying aboard the ship over the centuries of the journey, so that it is their distant descendants who finally arrive at a new world. Others imagine sending not people at all, but tiny robotic probes, accelerated to a fraction of the speed of light by powerful lasers, racing ahead to photograph and study a distant world and beam the images back across the years. None of it is possible yet. All of it lives on the far edge of plausibility. But the fact that we are even seriously discussing it, drawing up the blueprints, running the numbers, is itself a measure of how far we have come. And there is a deeper reason why finding these worlds matters, one that goes beyond curiosity and beyond the dream of travel, and it has to do with the long-term survival of our species. Earth is our only home, and for now it is a wonderful one, but it will not remain habitable forever. On timescales of hundreds of millions to a billion years, our own sun will slowly grow brighter and hotter as it ages, until it eventually renders Earth's surface too scorching for life. The same fate that may already be overtaking distant Kepler 452b. Long before that, there are countless ways a single planet can be a fragile basket to hold all of a species' eggs in: asteroid impacts, supervolcanic eruptions, the slow grind of cosmic chance. Every other living thing we know of is bound to this one world, and so, for now, are we. The discovery that the galaxy is full of other habitable worlds carries with it a quiet but profound implication. That there are, in principle, other places we could go, other homes that exist. The door is locked by the brutal mathematics of distance, but the rooms beyond it are real. And for a species thinking about its survival across the truly long span of cosmic time, simply knowing that those other homes exist, that we are not necessarily condemned to a single, perishable world, is a source of something like hope. But perhaps the most important thing these discoveries do is something subtler and more immediate than any dream of escape. They change how we see the planet we already have. When you truly absorb how rare and precious the conditions for life seem to be, how many things have to go exactly right, how easily a world in the habitable zone can turn out to be a frozen or scorched or suffocating ruin, You come away with a renewed appreciation for the extraordinary, improbable, almost miraculous nature of the Earth beneath your feet. We have been searching the galaxy for another world like ours, and in the searching, we have learned just how special this one is. The breathable air, the liquid oceans, the protective magnetic field, the stable and gentle sun, the perfectly balanced climate, the billions of years of unbroken biological inheritance that produced everything alive today, including you, all of it came together here, on this one small blue world, in a combination we have not yet found duplicated anywhere else. The search for other Earths has, in a strange and beautiful way, taught us to cherish our own. It is worth pausing to think about what the phrase "shocking discovery" really means in this context, because it is easy to be cynical about it. The internet is full of breathless headlines announcing that NASA has found a new Earth, only for the careful reader to discover that the planet in question is a superheated super-Earth orbiting a flaring red dwarf 1,000 light-years away, with no confirmed atmosphere and no real prospect of being livable in any human sense. The hype machine runs ahead of the science constantly, and it would be easy to conclude that the whole thing is overblown, that there is no real shocking discovery at all, just a steady drip of incremental findings dressed up in dramatic language. But that cynicism, I think, misses the genuinely staggering thing that is actually happening underneath the headlines. The shocking discovery is not any single planet. It is the entire pattern. It is the realization, built up over 30 years and thousands of detections, that habitable worlds are not freaks of nature, but a routine product of the way the universe makes stars and planets. The shock is in the abundance. It is in the fact that when you do the arithmetic, the number of stars, the fraction with planets, the fraction of those planets in the habitable zone, you arrive at a number of potentially Earth-like worlds in our galaxy alone that runs into the billions. That is the shocking discovery. Not that there is a planet where humans could live, but that there are billions of them and that we have only just begun to find them. And every so often, within that steady accumulation, there comes a finding that genuinely deserves the word shocking even on its own terms. The first time a planet's atmosphere was directly measured, the first time water vapor was detected in the air of a world in the habitable zone, the first tentative, trembling hint of a molecule that on Earth is made only by life. These are not hype. These are real thresholds being crossed, one after another, each one a thing that no human being in all of history had ever done until the moment it was done. We are living through a continuous unfolding of firsts, a steady procession of milestones that each, in an earlier age, would have been the discovery of the century. We have grown so accustomed to them that they barely register. But step back, and the cumulative weight of it is almost overwhelming. In your own lifetime, our species has gone from wondering whether other worlds exist to weighing their atmospheres and sniffing them for the breath of alien life. That is the shocking discovery. It is not a place. It is a power, the power to finally look and to begin to see. There is a beautiful detail in all of this that I want to make sure I share with you, because it transforms how you will look at the night sky from now on. We have talked about distant planets 100 or 1,000 light years away, abstract points on a map. But the truth is far more intimate than that. The next clear night, when you step outside and look up, look at any star, any bright point of light in the dark. The overwhelming statistical likelihood, based on everything Kepler and the other surveys have taught us, is that that star has planets. Not might have, almost certainly has. The discovery that planets are common means that nearly every star you can see with your naked eye is a sun with its own family of worlds circling it in the dark. The sky is not a scattering of lonely lights. It is a field of solar systems, each one a complete world unto itself, with rocky planets and gas giants and perhaps, here and there, a small temperate world with liquid water and a sky of its own. You are not looking at stars. You are looking at the suns of other worlds, thousands of them, visible to your own eyes, all of them almost certainly accompanied by planets we will never name and never see. That ordinary night sky you have looked at your whole life is, in truth, a sky full of other Earths, hidden in the glare of their suns, waiting in a darkness we are only beginning to learn how to pierce. And that, perhaps, is the most quietly revolutionary consequence of everything NASA and the world's astronomers have discovered. They have changed the meaning of the night sky itself. For every human being who ever lived before us, the stars were untouchable mysteries, lights with no known worlds attached. For us, and for everyone who comes after, the stars are suns, and the suns have planets, and some of those planets are the kind of place where, under the right conditions, a living thing could draw breath. We did not just find a planet where humans could live. We found out that the universe is built to make such planets over and over in numbers beyond counting, and that the only thing standing between us and them is a distance so vast it may take our descendants thousands of years to learn how to cross it if they ever do. The worlds are there. The homes are real. The question is no longer whether they exist. The question is only whether we will ever reach them, and whether, when our most powerful telescopes finally peer into the air of the most promising of them, they will find that someone reached them first, that on some distant temperate world circling a distant gentle sun, life, as it did here, found a way. So the next time you see one of those headlines, NASA shocking discovery, a planet where humans could live, I hope you will read it differently now. I hope you will understand both the truth and the limits of it. The truth is breathtaking. There really are worlds out there in the habitable zone, real planets where liquid water could flow, dozens already found and billions more waiting, some of them close enough by cosmic standards that we have given them names and pointed our telescopes at their skies. The limit is humbling. Being in the habitable zone is only the first step on a long and brutal road to true livability, and the distances involved are so vast that, for now, these worlds remain places we can study but not visit, destinations of the imagination rather than the spacecraft. Both of these things are true at once, and holding them together is the only honest way to feel the full weight of what we have found. We are not about to move to another planet, but we have proven beyond any doubt that other planets like ours are out there, and we have begun, for the very first time, to search them for signs of life. That is not hype. That is the most profound shift in our understanding of the cosmos since we first realized the Earth was not the center of everything. It is worth dwelling for a moment on just how the search is likely to deliver its greatest discovery, because the techniques we have talked about so far, the transit method, the radial velocity wobble, the reading of atmospheres in filtered starlight are powerful, but they are also indirect. In every case, we are inferring the planet's existence and nature from its effect on the star, never seeing the world itself. The faint dip in brightness, the subtle wobble of the star, the barcode of missing colors in light that graze the planet's edge. These are shadows and fingerprints, not portraits. And yet there is a holy grail beyond all of them, a technique so difficult that it has only just begun to be possible, actually photographing the planet directly, capturing its own light, seeing it as a distinct point separate from its star. This is called direct imaging, and it is staggeringly hard because the star outshines its planet by factors of billions. Trying to photograph a small rocky planet next to its star is like trying to photograph a single grain of sand sitting at the base of a blindingly bright searchlight, from kilometers away, with the searchlight pointed straight at your camera. The glare swamps everything, but engineers have devised ingenious ways to fight that glare. One approach uses a device called a coronagraph, a precisely shaped mask placed inside the telescope that blocks out the direct light of the star, while allowing the much fainter light of any surrounding planets to slip past and be recorded. Another, even more ambitious concept involves flying a separate spacecraft tens of thousands of kilometers in front of the telescope. An enormous, flower-shaped shade called a star shade, unfurled in the darkness, positioned with breathtaking precision so that it casts a shadow of the star directly onto the telescope while leaving the planet's light untouched. With the star's glare suppressed, the telescope could capture the planet itself, a single pale dot of reflected light, and then split that dot apart into its spectrum to read the gases in its atmosphere. The first time this is achieved for a genuinely Earth-like world around a sun-like star, it will be a photograph for the ages, a single faint pixel that represents an entire other Earth, captured in light that crossed the void to reach us. It will not look like much, a dim point against the dark, but that pixel will carry within it the chemistry of an alien sky, and in that chemistry may lie the answer to everything. Because the prize that all of this technology is ultimately built to capture is the biosignature, the chemical fingerprint of life. And understanding what a biosignature actually is, and why it is so tricky, is essential to understanding both the promise and the peril of this search. On Earth, our atmosphere is wildly out of chemical balance in a way that should not be possible without life. It contains large amounts of oxygen, a highly reactive gas that, left to its own devices, would quickly bind to rocks and other elements and vanish from the air. The only reason Earth's atmosphere stays flooded with oxygen is that life, plants, algae, photosynthetic microbes, continuously replenishes it, pumping it out faster than chemistry can remove it. An atmosphere rich in oxygen is, in a sense, a chemical scream, a state so far from equilibrium that something must be actively maintaining it. So if we were to detect abundant oxygen, especially alongside other gases like methane that should not coexist with it for long, in the atmosphere of a distant temperate world, it would be a powerful hint that something there is alive, actively churning the chemistry of the planet's air the way life churns ours. That combination, gases that should destroy each other, somehow both present at once, is one of the strongest biosignatures we know how to look for. But here is where scientists have learned to be cautious, even fearful of fooling themselves. Nature is cunning, and it turns out there are ways for non-living processes to produce gases that look like biosignatures. Certain types of stars and certain planetary chemistries can generate oxygen without any life at all, through the breakdown of water vapor by intense ultraviolet light. For instance, a world could have an oxygen-rich atmosphere and be utterly dead. This is the nightmare scenario that keeps the scientists honest. The false positive, the planet that looks alive but is not, the signal that fools us into announcing a discovery that turns out to be ordinary chemistry. This is exactly why the tentative hint of dimethyl sulfide on K2-18b was met with such careful, deliberate restraint rather than triumphant headlines from the researchers themselves. They know how easy it would be to be wrong, and they know that the first claim of life beyond Earth will be scrutinized more intensely than perhaps any scientific claim in history. To truly convince the world, we will need not one ambiguous molecule but a whole suite of evidence, multiple gases in revealing combinations, observed repeatedly, on a world whose star and chemistry have been carefully ruled out as alternative explanations. The discovery of alien life, when and if it comes, will likely not be a single dramatic moment but a slow, careful accumulation of evidence, building over years until the conclusion becomes inescapable. And imagine, for a moment, what it would actually mean to reach that point, to stand at the press conference where it is announced, with real confidence, that the atmosphere of a distant world bears the unmistakable chemical signature of a living biosphere. Not intelligent life, necessarily, not creatures or cities or signals. Perhaps only the equivalent of pond scum and bacteria, the simple microbial life that dominated our own planet for most of its history. But it would mean that life is not a one-time accident, not a fluke unique to Earth, but a phenomenon that arises wherever conditions allow, a basic feature of the universe, like stars or galaxies or planets themselves. It would mean that we live in a cosmos that tends toward life, that fills its habitable worlds with biology, the way it fills space with light. The philosophical and spiritual weight of that realization would be almost impossible to overstate. Every religion, every philosophy, every story humans have ever told about our place in the universe would have to be reconsidered in light of the knowledge that we share the cosmos with other living things. And it could happen with the next generation of telescopes. It could happen within the lifetime of someone watching this. The instruments being designed right now are designed precisely to make that discovery possible, and the scientists building them genuinely believe they are within reach of answering the question. There is a question that haunts everyone who thinks seriously about these matters, and it deserves to be confronted directly, because it casts a strange shadow over the whole hopeful story we have been telling. If habitable worlds are so common, if the galaxy is brimming with billions of places where life could take hold, then where is everyone? If even a small fraction of those worlds developed life, and even a small fraction of those developed intelligence, the galaxy should be teeming with civilizations, some of them far older and more advanced than our own. The galaxy is billions of years old, old enough that any spacefaring civilization, even one limited by the same brutal distances we face, could in principle have spread across it many times over by now. And yet, when we look, we see silence. No signals, no structures, no evidence of anyone at all. This unsettling contradiction between the apparent abundance of habitable worlds and the apparent absence of anyone living on them is one of the great puzzles of science, and no one knows the answer. Perhaps life is far rarer than the abundance of habitable planets would suggest. Perhaps the leap from simple life to complex, intelligent life is the true bottleneck, a step so improbable that it almost never happens. Perhaps civilizations arise and then destroy themselves, or simply never find a way to bridge the interstellar distances that defeat us. Or perhaps they are out there, and we have simply not yet learned how to listen properly, our search so young, and our instruments so limited that we have barely begun to scan the vastness. The silence could mean we are nearly alone, or it could mean only that we have just opened our eyes and have not yet learned to see. The habitable worlds we keep finding sharpen this mystery rather than resolving it. Every new temperate planet makes the silence a little more puzzling, a little more profound. Whatever the answer turns out to be, the search itself has already changed us, and it carries with it a kind of responsibility that I think is worth naming. We are the first generation in the history of life on Earth to know that other worlds like ours exist. That knowledge places us at a unique and strange position in the long story of our species. Everyone before us lived in ignorance of these worlds. Everyone after us will inherit them as established fact. We are the ones who get to feel the shock of the discovery freshly, who get to be alive at the precise moment when humanity learned it was not the only home in the universe. And with that knowledge comes a duty, I think, to take it seriously, to fund the telescopes, to support the science, to keep looking, to push the search forward so that the generations after us inherit not just the knowledge that other Earths exist, but the answer to the question of whether any of them are alive. We are the cartographers who began the map. It will fall to others to finish it. But the work we do now, the instruments we build now, the questions we choose to ask now, will determine how quickly that map gets completed, and whether the people of the future look back on us as the generation that opened the door, or the generation that glimpsed it and turned away. And so we come back at the end, to where we began, to that point of light traveling across the darkness, to that faint ancient glow carrying its secret toward our telescopes. When this story started, I asked you to imagine a planet out there with a red sky, with rain falling on rocks no human has ever seen, with an ocean sliding against a silent shore beneath an alien sun. I want you to understand now that this was not a flight of fancy. It was a description of places we have actually found. Proxima b, just over 4 light-years away, with its eternal twilight and its frozen night and its scorching day. TRAPPIST-1, with its 7 Earth-sized worlds wheeling around a tiny red ember, sister planets close enough to hang in each other's skies like moons. K2-18b, possibly a single endless ocean beneath a hazy sky, exhaling a chemical breath that just might be the signature of something alive. These worlds are real. Their light is reaching us right now. And in that light, we are learning to read the chemistry of distant skies and to ask, for the first time in the history of our species, whether we are alone. The honest truth is that we do not yet know the answer. We have not found life beyond Earth. We have not found a world we can travel to. We have not found a second home waiting for us across the void. What we have found is something that, in its own way, may be even more important. Proof that the universe is full of possibilities, that habitable worlds are common, that the conditions for life arise again and again across the galaxy, and that we now possess, for the very first time, the tools to go looking for whatever might be living on them. We have crossed a threshold that humanity stood at the edge of for its entire existence, the threshold between wondering and knowing. And on the far side of that threshold, the questions only grow more thrilling. Is there life on K2-18b? Could anything survive in the twilight of Proxima b? Is one of the 7 worlds of TRAPPIST-1 home to oceans, to weather, to the slow stirrings of biology? We do not know, but for the first time we can find out. And the answer, whatever it is, will reshape our understanding of ourselves and our place in the cosmos forever. So the next clear night, step outside. Look up, find a star, any star, and remember that it is not just a light. It is a sun, and almost certainly it has worlds, and somewhere out there among the countless suns scattered across the sky, there are planets sitting in the gentle warmth of their stars where the temperature is just right, where water could flow, where a sky could be blue or red or some color we have no name for. We have found them. We have named some of them. We are reading their skies. And though they remain, for now, impossibly far beyond our reach, the simple fact that they are there, that we are not a singular miracle but one home among billions, is perhaps the most profound and humbling discovery our species has ever made. The universe, it turns out, is full of other Earths. The only question left is whether anyone is home. And in our lifetimes, against all the odds of all the long ages of human ignorance, we may finally find out. We are not alone in having a home. The galaxy is full of them, and somewhere out there, on a world we have already found, or one we are about to, the answer to the oldest question we have ever asked is waiting in the light, traveling toward us across the dark, growing closer with every passing year. All we have to do is keep looking, and we will, because we are the species that looks up. We always have been. And now, at last, after all this time, we are finally beginning to see what is looking back.